My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all in our International Physics webinar. So today it's our 78th International Physics webinar, and we have successfully completed our 77 International Physics webinar. So good evening to all, and hope you are well and safe from Corona pandemic. So I think you have already come to know that we have arranged this webinar to encourage our students and motivate our students in this Corona pandemic situation. So you know that we cannot continue our normal academic program inside the campus due to the Corona pandemic since March 2020. So we have to start our online program. You have already come to know that our Department of Physics, Pabna University of Science and Technology, has started its online program, including online classes and online international physics webinars. So we are trying to adjust with this new normal situation. So today is very important day for our department. Today I would like to welcome you all through a joint session between the Department of Physics, Pabna University of Science and Technology, and the Indian Institute of Science and Education and Research, Kolkata, India, in Material Science. And we have with us here today Dr. Amit Ghosal, sir, Professor Physical Science, Indian Institute of Science and Education and Research, Kolkata, India, connecting us through online from India, and he has already connected with us. So I'd like to welcome our speaker. So good evening, sir.
And welcome to thank you so much for having me here. It's my pleasure to be here. I would definitely look forward to this event. So I have never been to Bangladesh, and I always wanted to be there. But this is my first attempt to connect with people, scientists in Bangladesh, and young students in particular. I look forward to this session.
Thank you, sir, for accepting our invitation, and hopefully in near future, after the COVID, we will definitely invite you for face-to-face session in Pabna. So thanks for accepting our invitation, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, and I think our student will learn a lot of things by your session. So for those who are new, I would like to inform that we have divided our webinar into three parts. First, I would like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion time. In that time, actually, anybody can join with us, and you can ask question by commenting also. So you have already come to know the title of this today's International Physics webinar, and title is "What's the Matter with Matters?" And our speaker is Dr. Amit Ghosal, sir. He's currently working as a professor physical sciences in Indian Institute of Science, Education and Research, Kolkata, India. So we can see his educational background. He has completed his bachelor degree from Jadavpur University in 1993 and master's degree in Indian Institute of Technology, Kanpur in 1993 and PhD in 2001 in theoretical condensed matter physics from Tata Institute of Fundamental Research, Mumbai. So we can see his professional experience. So he's currently working as a professor at IISER, Kolkata, but he has already did his postdoc and associateship in Duke University and McMaster University and section postdoctoral associateship, and then he joined as assistant professor as a IISER Kolkata in 2008, and he worked there as assistant professor in IISER from 2008 to 2013, and as an associate professor at the same place in from 2013 to 2018. So you can see his awards and honors. So he got awards and honor from different organizations. So you can see from APS IUSST Professorship Award in 2018 from the Indo-US Science and Technology Forum, and David Saxon Postdoctoral Fellowship from Physics Department, USA 2005, and SARC Net Prize Fellowship from SARC Net Canada in 2001, and General Proficiency Medal from IIT Kanpur in 1995. And you can see his research area. His research focuses primarily on condensed phases of matter, in which the complex interplay of interparticle interaction and intrinsic disorder in the material leads to intriguing emergent phenomena. And you can see his ResearchGate ID, and his ResearchGate point is 25, and this is his recent published paper. So thanks all for all of your patience. Now it's time to go to our speaker. So, sir, I'd like to welcome you again. So it's your time. You can start your session, sir.
Okay, thanks so much, Professor Das. I mean, it is thanks so much for such a kind introduction. I hope I'll be able to do justice to this presentation. And yeah, so another thing I would certainly like. I was quite interested, but I thought I'm not quite prepared, which is giving a talk or presentation in my mother tongue, which is same as your mother tongue. I mean, we share that. I have never tried that, so that's the reason I didn't venture into it. But probably in some time in future, I would learn how to make science presentation in my mother tongue. Okay, so that apart, so let me now go to the talk. So I think can you see the talk now, or should I
Yeah,
have
we can
to
see. We can see
make
the
full?
full screen, sir.
You
No,
can
no, we
you
can
can
see.
see the full
Yeah.
screen. Okay, so there is something. Yeah, so something went wrong, I think. Yeah. Okay, so let me
Now it's
make the
okay.
point. Let me make the pointer, and that's okay. Yep. Okay. So the title of my presentation is "What's the Matter with Matters?" I mean, this is just a thought of putting some kind of uh, catching attention title. So essentially, what we are going to do is that we are going to do an overview of the broad area of condensed matter physics. I'll talk about many excitements which are keeping this field very active, and the field had been very, very active for a very long time. I'll speak about that. But then I'll focus on introducing you to that. And this presentation will be mostly for younger students. Many experts might have better familiarity of the subject than what I am putting here. Please excuse me for that, but I still hope that you will find this useful and entertaining, if not anything else. So with that, let me start. My name is Amit Ghosal, and I am a faculty at Indian Institute of Science, Education and Research, Kolkata. IIACR is how it is known. So, what is condensed matter physics anyway? So that's the question we might often ask. But see, it is always difficult to define things. I mean, in science, we always like to define things, but if you ask how to define condensed matter physics, it is difficult. So one possible approach that people have taken is to describe to sort of classifying the different branches of physics based on length scale at which it operates. So before I get to that length scale, which is the picture I will explain here, but let me give you a quick and easy answer to the question: is that this is the study of, condensed matter physics is study of macroscopic properties of dense assembly of constituent particles. Mostly we talk about electrons when we talk about constituent particles, which are formed by placing atoms very close to each other. So this part, dense assembly of constituent particles formed by placing atoms very close together, this essentially means condensed phase. So condensed matter physics is study of condensed phases of matter like solid, liquid, and so on and so forth, primarily. And then other phases are also there, like gas has a low density, but that's also can be thought as a condensed phase. So phases of matter, and we are going to look into what phases of matter means. So just a quick advertisement for this branch of physics, that more than 40% of physics Nobel prizes in last 40 years or so, and sort of a similar fraction in the past 10 years. That means around 40% in last past 10 years also. So it had always been, so this is just to say that this subject had been always active, or more or less equally active over a long time, that such prizes are awarded to condensed matter physics. Now, please don't think of it as a sense of, it's not that this subject is interesting because so many Nobel prize has gone into the subject. I hope I'll be uh, able to give you the impression that the subject is interesting, and that's why this statistics stand by the subject. Okay, so with that, let me try to tell you what I mean by classifying branches of physics by length scales. So So here you see this is a length scale that I am plotting along the horizontal axis, which is the length scale given in meter, let's say. So here length scale ranges from, I think this is 10 power minus 40 here. I mean, very small length scale, 10 power minus 40 meters. And this is the very large length scale, which is 10 power 40, or this is 10 power 30 here, if I go by this division, meters. So which is essentially a very, very large scale. So what is this scale? So this means that if I take a branch of physics and if I typically consider particles, by particles I don't really mean real particles, I mean which are considered as particle for that particular field, which are at a typical distance of that length scale. So that means here if I put the subject cosmology, which is one branch of physics, which deals with galaxies and universe and all that, so there, each particle, like a galaxy, is like a particle, and they are separated by a length scale or by a distance which is like 10 power 30 to 10 power 40 meter. Okay, so that's what I mean length scale. The typical particle, typical constituents which make up the subject, they are at a distance of length scale of that. I mean 10 power 30 to 10 power 40. So if I come down in length scale about 10 power 20, we will have 10 power 20 to 10 power 30. I mean, some overlapping region. There will be astrophysics or astronomy. I mean, where the particles are like planets. I mean, there the particles were like galaxies, and the collection solar system. I mean, is one particle or one constituent object. So if I come down to things like where the particles are like planets, the length scale will be down. And then there is a wide region of classical physics. What mostly come here is what we call geophysics, the art physics, art science. And then come a range which is 10 power 0 meter, that means 1 meter, down to 10 power minus 10 meter. So 10 power minus 10 meter, as you know, is 1 angstrom. So that is the interatomic spacing typically. So this is the range where condensed matter physics operates. So as I have put by these braces here, so this is the area of operation for condensed matter physics. So here we want to describe particles or constituent objects which are separated by a distance of 1 meter all the way down to one angstrom, which is the, as I say, that this is the atomic length scale. That's the smallest length scale where condensed matter physics operate. So I wanted to emphasize here that this is the length scale. So the subject is very interesting because this is the length scale that we can see. We can see by naked eye in this side, and we can see by some kind of a fancy binocular, if you want to call it, some microscope. I mean, some fancy microscope, not the regular one that we often play with which you can see the object. Now, if you go down, I mean, you will go down in this length scale. There will be a range of what is normally covered under nuclear physics. And then probably, again, overlapping with nuclear physics, you will have a length scale of 10 power minus 30 or so. I mean, maybe between 10 power minus 25 and 30, you will have high energy physics, which is a very exciting branch of physics. I mean, so that's one. I mean, which talks about fundamental particles. I mean, so that, and then if you go down to the smallest length scale that physics try to access or physics try to describe, at the scale of 10 power minus 40, you have what is known as string theory. Sorry about this black patch, which is hiding the name. Yeah, so now you can see string theory. So there, the fundamental particles, I mean, particles within code, fundamental constituents are like some strings, and they vibrate, and it is believed that vibration actually brings about many interesting and exciting aspects of physics. I mean, at the smallest length scale, I mean, most fundamental length scale. So that is string theory. So the main point of this picture is to say that based on different length scale, you can sort of classify different branches of physics, and condensed matter physics lie in that particular range, which is quite accessible to our perception. I mean, perception in regular English sense. So that's where condensed matter physics is. So actually, this length scale is essentially inversely proportional to energy scale. So this is the smallest length scale goes to a very, very high energy scale and opposite in this direction. But let's not worry so much about it for now. So let me just continue a bit more on this length scale business to say that actually the different branches of science can also be classified by and large in a similar manner. So here there are different branches which are oftentimes overlapping. So like this is the large scale that I was talking about. It is about 10 power 30 meter, which is the universe scale. I mean the cosmology area that we talked about. Galaxies and atmosphere, and then it becomes, so this is the range of astronomy. I mean so here what I'm saying is that this is the range. That means in this range the astronomy operates. This is this brown patch. Then the biology operates in the scale which is here, which is roughly same as where condensed matter physics operates, roughly speaking. Chemistry works for a little smaller length scale, I mean, which is here of this thing. I mean, as I say, these are always overlapping, as you can see. Geology works here. I mean, basically above condensed matter, which is here. Condensed matter was for the human size, 1 meter or 10 per 0 meter. Atmospheric science has a wide range. But what is very interesting is that if you think of physics, I mean, biology, chemistry, geology, these are all different. Atmosphere is all different branches of science. So if you think of physics, that actually is the subject which operates on all length scale, because just in the previous picture, we have seen that there are different, I mean, if I go to this one, I mean, physics operates over the whole range. So this is somewhat satisfactory or gratifying for us as a physicist. You can think of it as some kind of a propaganda for physics, but I can't help it. I make my living by doing physics, so I think I'm allowed to do this kind of propaganda or promotion of physics, that it operates of all length scales. Okay, so beyond length scales, condensed matter physics is also characterized by something which I was sort of trying to sort of hinting to, is that it operates at a complex scale. So it describes phenomena at a complex scale. By complex, I mean the complexity that we can perceive with our own sense. I mean, in the sense that this is something that we can access. So just to give you an idea, so here I have written it. It is accessible to experiments with relative ease. I mean, many people try to say that one can do a tabletop experiment in condensed matter, which is essentially not so easily accessible for any other field. It is not always tabletop, but it is much more tabletop than many other branches of, compared to many other branches of physics, because it is the accessible length scale where it operates. So for example, by complexity, what I mean is that suppose you have, you want to describe hydrogen atom, I mean, which is the simple atomic physics, so then you talk about 10 power 0, I mean 100 power 0, which is like one atom. I mean, that's the hydrogen atom. You want to understand that, and you know the quantum mechanics of that, or you learn that as a textbook example of quantum mechanics. You want to understand that. That's simple enough, one atom. Now, once you want to go to a little bit more, I mean, let's say a regular metallic property like superconductivity, in some simple sense, superconductivity. I mean, these are called metallic superconductors, which are very well described by what is known as BCS theory of superconductivity, or Bardeen-Cooper-Seyfert theory of superconductivity, which is a very, very celebrated description of a particular phenomena. I'll not go into that now. So to describe that, you need about 100 atoms, I mean, of niobium, let's say. So 10 power 1, 100 power 1 means 100. Then if you want to go to 10 power 4 atoms, assembly of 10 power 4 atoms, you describe what are called two-dimensional electron gas, which is formed at the interface of gallium arsenide and gas, aluminium gallium arsenide heterostructure. I mean, in the junction of that, you form a two-dimensional electron gas, where you can understand a bunch of physics involving something is written here. These are for now just names, fermions and fractional quantum Hall effect. Quantum Hall effect is what is a particular area of condensed matter physics, large area. So to understand that phenomena, you need like 100 square or 10 power 4 atoms. So you see the complexity is increasing for 10 power 0 to 10 square to 10 4 to 10 6. I mean, that you require if you want to describe some alloys. I mean, so here it is here is atom, here it's a metal of same element. Then we went into some kind of a molecule assembly of uh, 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 different elements, so which is molecule, and then we go into alloy, which has a larger structure, and like uranium alloys, they describe heavy fermion physics or heavy electron physics. And then if you go to even, I mean, you want to understand cuprate perovskites. I mean, this is perovskite is the structure of material which is layered material. You see, is a large. This is a picture of a unit cell. This is also a picture of a unit cell. So it is much bigger unit cell, and that's why you require much larger number of particles which are called copper oxide superconductors or high temperature superconductors. They're also superconductors, but very different from what I described here as niobium. So this is something which is really an area of active research. I don't want to get into that, but the main point is that with increasing number of the atom or element or constituent particles, you increase the complexity. It is not obvious why complexity is increasing that way. So for that, you have to really look into the phenomena that is associated here: atomic physics, then simple superconductivity, then fractional Hall effect, and heavy electron or heavy fermion system to high temperature superconductors. The materials become more and more complex for reasons. Maybe this I'll make some comments about it towards a later point. But so the point, yeah. So this is what it happens for condensed matter physics, that it operates at complex scale, and you can uncover the complexity step by step by studying different parts of condensed matter physics, so different areas of condensed matter physics. So now this complexity or enhance of complexity is related to what are called emergent properties, which I've written here. It is written here example of emergent phenomena. So emergent phenomena is something which is a very popular buzzword for people working in condensed matter, and I'll give you what it means. I mean, it's not difficult, simple. Which says that system containing many particles exhibit properties that are special to such systems. Such properties are fairly insensitive to the details, and they are called emergent properties. Now, if I just give you the definition as written here, it might occur very fishy, because there's some property which is special to some system. I mean, what's so big deal? I mean, what's the generality of such a statement? And I'll explain what they mean. Which is that you take two different sets of the same amount of H2O. I don't know why it is missing here. It should be there. H2O, which is water molecule. You take the same amount of water molecule in two different beakers, let's say. Identical beakers, identical amount of H2O. And they, of course, follow the identical law. However, they might have very different physical properties. Like one can be ice, as written here, and the other could be water. So the fact that one could be ice versus the other could be water is a property which is arising because you are seeing many such H2O molecules as an assembly. So these phases, when you observe a phase, that's a property associated with the fact that properties of a phase emerge is a result of what are called emergent properties, and occurs just because you have many particles collected in one place. And that's how that occurs. How such properties occur in the system is the subject of subject of study for condensed matter physics. So just take an example. So if you had one molecule or maybe 57 molecules of H2O, does it give you a sense of weighting? I mean, wetness. I mean, the wet nature that is associated with water. If you touch water, you feel it is wet, right? But that wetness is not there if you have a small number. I mean, of course, few molecules or one molecule of H2O cannot give you a sense of wetness. So that such properties are emergent properties, which are generated because of assembly of many particle systems. So that's something which is very important, and that's what is under the purview of condensed matter physics. So now here I talked about ice and water. So these are, I mean, sorry. So these are example of different phases as written in the bottommost line, that two different phases of H2O. So phases are of extreme importance in condensed matter physics. What one can say that the condensed matter physics is a subject that deals with the understanding of different phases of matter, as well as the transition between these phases. So that means a phase can transit to other, like a melting of ice, then it goes from a solid phase, which is ice, to a liquid phase, which is water. So such things are called phase transitions. I mean, this is what is written here. So in very brief, this is what the broad domain of condensed matter physics is. And so then we need to know a little bit more, and let me go to that. So broadly speaking, condensed matter physics is divided into two parts. One is soft condensed matter, and the other is called hard condensed matter. So now this soft and hard is, I'm not sure how good a terminology these are. I mean, it might just say that the physicists are generally little unimaginative with the names. I mean, naming the field. There is nothing soft about soft condensed matter, or it's not that hard condensed matter deals with hard problems. I mean, there's no such thing as that. So the way they are distinguished is that I mean, if you look at the soft condensed matter physics, as I have written, I'm not taking my cursor down there because the black patch will appear. Is that the richness of soft condensed matter physics is contributed by classical physics. I mean, so it's a classical physics which is of paramount importance for the interesting phenomena that you see, or many times it is dubbed as classical. I mean, application of classical statistical mechanics. So, on the other hand, I mean, thermal fluctuations is something which determines many of the interesting properties. I mean, thermal fluctuation is sort of a jargon, but I will probably not make much more comment on that. On the other hand, hard condensed matter is the one where the richness is contributed primarily by the quantum physics, or in other words, it's the quantum fluctuations which can drive many interesting properties of the field. So quantum fluctuation and thermal fluctuations are the two words I have used here. Don't worry if you don't understand, but essentially it is the quantum mechanics dominated area, whereas this is the classical mechanics dominated area. So this is good enough for now for our purpose. Okay, so now if you are talking about phases, so it is good to have an idea of many different phases that we encounter within condensed matter, and this is just a partial list. The list can go on forever. So as you can see that there are many phases like solid versus liquid. So this is one set of classification based on the rigidity of the material. Then from the magnetic aspect, if you want to classify different phases, you can have paramagnet where the magnetic moments are completely random, then ferromagnet where all magnetic moments are aligned in a particular direction, antiferromagnet where all magnetic moments are aligned, but they're they're oppositely oriented next to one another. So that's antiferromagnet. Ferrimagnet is something similar to antiferromagnet. I mean, but however, in antiferromagnet, the up and down magnetic moments cancel each other exactly. In ferrimagnet, they don't. I mean, basically, there is a net magnetic moment in one direction. So, and then you can talk about metal versus insulator based on electrical transport properties. You can you can have superconductors. So there are always, again, you might little unimaginative aspect of naming. in the sense that you just add super. So this might mean something, that it is a conductor just like metals. However, there is something superb about being conductor in this case. So so those are superconductors. So in other words, what happens, so you might know already that these are zero resistance. So this is absolutely fascinating conductance that occurs in these materials. Their fluid features super again becomes super fluid. So these are fluid, but it has a fantastic fluidity, super fluid. And then there are super solid. I mean, which is absolutely bizarre name in my opinion. So super here, super does not qualify solid. There's nothing superb about these solids. It's actually super fluid that is solid also. So this is a very bizarre concept. And they have a true super solid has not yet been found in experiment, but physicists believe that they do exist. I mean, they can exist. Not that they do exist, they can exist. So it's a challenge to find them existing. So it's just saying that it is something which is like a super fluid but solid at the same time. So that kind of a thing. And then there is dielectric, which are essentially a class of insulator. I mean, insulating material, electrical insulator. So dielectrics are electrical insulator, but they are dielectric because of the polarization, some energy storage, like in capacitor and all that. So there are many different phases possible. All are characterized by set of properties, and one can see transition from one to another. Okay, so now let us go into a little bit more detailed understanding. So I said that there are transitions from solid to liquid. So solid is here. So solid is identified by placing atoms, which is this yellow balls that you can see, in a very regular pattern. So like here, this regular pattern is called lattice, which is here, it is called a cubic lattice. You can see the cubic structure in it. So it's a very, very periodic, infinitely periodic array where atoms are arranged at the vertices of this skeleton. So lattice is the skeleton. The lines which are shown, they are not real lines. I mean, you don't see lines, but there's imaginary lines where the vertices are only real, where the atoms sit in a material of a solid. Sorry, what happened? I'm so sorry. It just went straight to the end. Yeah. So that is a solid, but then it transits by increasing temperature to a liquid, where you see this is the atom again, and there's no lattice, of course, underlying lattice. They're all wandering around everywhere. So that's the structure of a liquid, and such a transition is called melting transition from solid to liquid. And this is how it happens. As you increase temperature, solid, which are arranged in a very regular periodic pattern, goes into something which is randomized. You can actually heat it up more, and you go to a gas which is not fundamentally different from a liquid. There is no ordered pattern that you see in a solid. It's just that the density is far less. So basically, atoms move apart from one another even more. So similarly, one can talk about a transition in a very different material. So earlier one that I have talked about is a solid to liquid, like a ice to water transition. Here one is talking about a transition in a magnet. So magnets also undergo phase transition, and magnet, this is horseshoe magnet. You must have seen that, and you know that in magnet you can define North Pole and South Pole. I mean, they attract each other, North Pole and South Pole, and every magnet will have two poles. I mean, you cannot break down. You can break down this magnet, and you can make many more North Pole and South Pole. You can break it down to the level of having what are called magnetic moments. So you can think of a magnetic material is made up of magnetic moments, which in a ferromagnetic state, they're arranged in this way. So back to back, in tandem, there is this little magnet which you can call magnetic moment. So a south pole is attached to north pole, and so on and so forth. So all such little tiny magnetic pieces which are magnetic moment are arranged in a very nice ordered manner in ferromagnet, just the way the atoms were arranged in a very regular periodic and regular manner in a solid. Similarly here in ferromagnet, and they get completely randomized in direction when you go to a paramagnet. So you start with this at very low temperature, you heat up, you get to a paramagnet state, just the way you heat it up and you go to a liquid in a quite similar manner, from an ordered pattern to something which is not ordered at all. Actually, the critical temperature where that happens is called the Curie temperature, which is just an information as written at the bottom of this page. But what is important, that just like the previous one as well as here, so it seems that there is, I mean, these two phases are identified by a sense of ordering of this little magnet, or ordering of molecules in a H2O, in ice as opposed to in water. So this propensity of being ordered is what is that actually that property is turned into something called an order parameter. So what one believes, that there is something called order parameter for a magnet, that is called spontaneous magnetization. I mean, it is good to just say magnetization. So that magnetization is finite or large in this phase ferromagnet. How large, that depends on at what temperature you are at, and this actually goes down. So if you plot it as a function of temperature, so this is the order parameter, which is magnetization, that has a value something which is large here, and as you increase temperature it goes down and finally it disappears at some point. So that's the point which is called a Curie temperature. So the point is that there is something which you can call order parameter, which is always found in this kind of phase transition, which goes from a finite value to a zero value as you go from an ordered state, which is here, to a state which is disordered. I mean, that's how you call it. So here is a picture that in very low temperature, they are very nicely ordered. If you increase temperature, they're still ordered. By and large, you can see there is an ordering in a particular direction. So these arrows are like this little magnet. I mean, here I use two colors. Here there is no color. You can think of one color, red, to be the one with arrow. So that's the sometimes people call them spin, but we don't have to worry about those details at this point, which get completely randomized beyond the Curie temperature, which is here. So one can take such analogy of phase transition to more exotic situation, and so like people indeed believe me. People study in condensed matter, and this is the part of soft condensed matter, which is a traffic jam model. So how to model a traffic jam? So for example, you can think of this as a road in some highly developed countries where people are all very civilized. They're going in a very ordered manner in a highway. I mean, this is actually pretty more like a traffic jam only, but doesn't matter. They're at least ordered, versus some road condition that at least I see in my city almost all the time. I don't know what you see at your place, but it's a very chaotic traffic in most parts of my city, Kolkata. I mean, which is very high density of people, so it's always jammed up everywhere. So people indeed study or model traffic jam. How to understand traffic jam, which is how does it go from an ordered traffic to a rather chaotic traffic. And as you can see that these are a much larger system. So constituent particles are like cars here, I mean, which are much larger. I mean, I mean, here the typical distance is several meters. So this is the regime of classical statistical mechanics, right? I mean, here you can't think of quantum effects to be very important because these are much large system, I mean, for obvious reasons, because quantum mechanics operates at a very small length scale, and the other opposite length scale is the regime of classical mechanics. So the point is, and then I can go even further in statistical physics or classical or soft condensed matter area. People study what called self-organized criticality, where what you do, I mean, this is something that you all played perhaps when you were little. I mean, you go to a sea beach and then you try to make sand piles. I mean, you just drop sand from top, and then there is a conical structure which will be created. That's the sand pile, and that grows in height. However, if you keep adding sand, it can grow only up to some distance, or what people say that it can grow only up to some critical angle. Once you pass that critical angle, which is this angle, then if you add more sand, it will not stay. I mean, it will not just keep getting taller and taller. So there will be avalanche, and so avalanche, and then the critical size will remain. So it seems that the system is self-critical. I mean, in the sense that the system knows by itself that there is a critical angle beyond which you cannot add more sand. So this had been a prototype of a bunch of different areas, and these are called sand pile models. I mean, people try to understand how does the self-organization of the structure to a critical value occur. So critical slope, I mean, that's it. Yeah, so that's a study, and that has implications for many other self-organized systems. So like what one is showing here is the river network. So all these pictures are network of river. So how is a particular network of river created? What is the statistical description? So that people study. So this is the actual river network, and this is the predictions, and people try to explain the critical properties of this system. Even that comes under soft condensed matter or classical statistical physics. So the other important aspect, I mean, quite profound aspect, I would say, is that there are linkage between different phase transitions. So, for example, you can see that I talked about solid to liquid transition, where it goes from ordered to disorder, and similarly in traffic jam model also it goes from ordered to disordered phase. So it seems there's some universality in the phenomena, in the sense that this ordered to disordered transition, if occurs, it will occur because of some fundamental reason which must not care so much about the details of the system. I mean, whether it is solid to liquid, I mean, melting of ice, or it is a traffic jam model, or it is a ferromagnet to paramagnet transition. So that's the beauty of physics, that it goes far beyond what you really see outwardly, to something which might be much more fundamental reason to sort of tie up a wide range of phenomena. That's true generally for physics, and certainly in condensed matter physics we see that all the time, many times at least. Okay. So the last one comment about this class of phase transitions that we are talking about, I mean, which goes from an ordered state to a disordered state, and this may appear very not so obvious, is that they are actually connected by symmetry, and this is a very, very old and profound concept of physics. Symmetry, as you know, so like if you have a butterfly, and if you reflect the butterfly about an axis which is given by this red dotted line, it will fall exactly on top of each other, and that's the meaning of symmetry. I mean, in this case, butterfly has a reflection symmetry around this axis. So basically, symmetry means that if you perform some operation, the system remains unchanged. So that's what symmetry is. So like here you see the Taj Mahal, and it is the reflection on water. It is not an exact symmetry. You know that this is the actual Taj Mahal, and this is reflection on water, but this is an approximate symmetry. So symmetry, approximate symmetry, all these have various different consequences for phase transitions that we talked about. In particular, what is known that whenever you have an ordered to disordered transition, this is always associated with a breaking of symmetry. So you break a symmetry of the system, and when you undergo a phase transition. So you can talk about it for solid to liquid. I mean, there is a symmetry that you can see, you can easily translate, or you can certainly see the symmetry in this picture, that if you translate by some amount, excuse me, the solid falls on top of each other. So that's the symmetry, and that symmetry is lost in the liquid. So for some technical reason, liquid is called the system of higher symmetry, whereas solid is called the system of lower symmetry, because it is more difficult in some sense to bring it back to itself. I mean, you have fewer operations than what will be here to bring the system back to itself, and that's why it's called lower symmetry. So much of the transitions that I talked about so far has a transition between has to do with a breaking of some symmetry or the other. And the other thing that we should know is that there is a notion of phase diagram, which is just the way you draw the maps of various parts of the world. I mean, so here they're color coded as the continent, like Asia, Europe, Africa, Australia, South America, North America, etc. Different color map. So similarly, what you do is that for different phases of matter, you color them in different way. I mean, coloring is not important, but you divide them by line just the way you have divider of different continents. So one part is solid, one part is gas, and then there is a liquid part. And I said that liquid and gas are similar to each other because you don't always have to go through a transition. But that's more of a technical statement. So let's not get into that. But the main point is that when you talk about a phase diagram, I mean, much of the goal of condensed matter physics when it studies a particular material is to find out its phase diagram, because once you know the phase diagram, you have far better predictive power. That if you like in this particular pressure, if you increase the temperature, then it is this precise point where the solid will yield into a liquid, and then liquid becomes gas at this particular value of temperature. So you have a predictive power, and that is just as I said. I mean. Jokingly, it is marking territory. So you say that this is my territory as a solid, this is my territory as gas. So similarly, more complex material will come with many different possible phases. So this is one example of phase diagram of high temperature superconductor, so which is in terms of temperature and something called doping, density of a particular material. I mean, let's say oxygen doping, it's called. Density of charge carrier is probably the best way to say it. And then if there are many different phases, antiferromagnetic here, this is some phase called pseudogap phase. One doesn't really know it very well. So is this, which is a metal, but there is an additional clarifier called strange metal Fermi liquid, and there is a region of superconductivity. So these are phase diagrams. So the thing is, more complex a material becomes, more phases you will encounter. This is true for not only high temperature superconductivity, but many other objects like transition metal dichalcogenides has many different phases, and then there are other materials like colossal magnetoresistance perovskite material, so which have very multi-phase diagram. So when we are talking about them, so let me quickly tell you. So this is, I mean, all that I have described so far have been understood over years and is under well control. I mean, people have understood metals, for example, at a very long time. I mean, this development has taken place starting from early 1900 to, let's say, 1970, maybe early 80s. By then, the subject was very well developed. But then after that, what are more modern day surprises in condensed matter has to deal with more interesting stuff. So, for example, people talk about strongly correlated systems. So we talked about metal as a phase. So what turns out that metals can be very well understood just by considering it as a gas of free electrons. Basically, by free electron, I mean they don't interact with each other. You might say this is weird because I knew that electrons repel each other, like charges repel each other. They indeed do. They indeed repel each other. However, it turns out to describe the properties of metals, such repulsions are not important. And in physically, such repulsions can be less important for various reasons. I mean, we don't have to get into that, but that's something which is very well documented. But we also knew, I mean, we also learned in this period, this long time period, that when we turned on interaction between the constituents, we describe other interesting phases like superconductors and magnets, etc. But when you really wanted to bring into the table the real negative charge electrons, which have a very strong Coulomb repulsion when they're close by, when you bring it into the table of the understanding, it seems that you find many unusual properties. So classifying such unusual properties are called called the not classification. I mean, so such unusual properties that contributed or studied in a subject which is called strongly correlated electronic system. So basically, if you want to talk about the strong electronic repulsion, when you take into account many unusual things happen. For example, it can turn a perfect metal into something called insulator, called Mott insulator in this case, by the name of Professor Sir Neville Mott. And then and in such an insulator, electrons which are, let's say, on a lattice which looks like this square object, electrons are in this region, and such lattices are made of are actually the planes of what are called high temperature cuprate superconducting materials like lanthanum, strontium copper oxide, which has a very complicated or complex looking unit cell structure. So there they sit on these planes which are like squares, and electrons sit on oxygen which are like this. There are these arrows. You don't have to worry too much about arrows, but just to give you an idea of what they are called spin. Electron has spin, which is like an arrows. So they arrange themselves in a particular manner, which, looking at the spin orientation, you would call them antiferromagnetic. But the main point is that they're insulated because they repel each other so strongly that they are in a locked situation under normal circumstances. However, what happens that and that's why, because they are locked, they cannot move around. There is no movement of electrons, and hence they're insulated. They cannot carry current. On the other hand, if you somehow pluck out an electron and thereby make a hole, so like this one, you see, so there was an electron which is missing from here, so that is called a hole. I mean, absence of electron is called a hole here, which somehow can move around very well. I mean, it actually moves around much better than what an electron would have done in a regular metal. I mean, so that's what that's the thing I've written here in italics, and this thing that they superbly move around, giving rise to what is called an unconventional superconductivity or high temperature superconductivity, which actually causes a very complex phase diagram like this, as I said before. Okay, so now I will go into something, but at this point, it is a good idea to find out how much time do I have. Pretam, can you give me an idea about time?
You can carry on, sir. No problem. You can carry on, sir. We have about 15 minutes.
15 minutes. Okay, good.
15 minutes.
Okay, very good. Thank you so much. Okay, so now, so remember, so now you might ask, why do I study these strongly correlated electronic system? The reason we have to at least appreciate, which is the following: that firstly, these strongly correlated electronic systems are real materials. I mean, real materials show these properties. Much of these properties, like this high temperature cuprate superconductor we talked about here. So then, because it occurs in nature, we have to understand that. But I think the fundamental reason is actually far beyond that. So, which is the following: that with the extreme control and ultra tunability on experiments carried out by our friends in different branches, like in industry, in technology, in chemistry. I mean, we are at a position now where we can develop. I mean, so this has been done over last few decades. We are in a position to develop or fabricate materials which will perform the task we want it to perform. So we can make these materials our slave, if you want to use the word. I mean, I don't want to use it in a bad sense. So what we want to do is that we want to make materials which will solve environmental and energy problems. So materials which are not just something which nature has given to us, but we will create materials. So that's the direction where in last about couple of decades, people, I mean, we have made enormous progress. I mean, as a community, and that makes us very greedy and think that so now, if you want to make materials which will be useful, then you have to attach some properties which are unusual, right? If properties were just usual, they will perform usual they'll perform usually like a regular metal which is given to us by nature. So we want to change the properties, tweak the properties in some way and make it useful for us. Such materials got a particular name, and we must all know about that, or we hear about that. They're called smart materials or functional materials. Functional materials because they are created or they are being fabricated for performing a particular function. They're called smart materials, just the way we call smartphones or smart watch and all that. So basically, so their existence are because of certain performances. Hope with the hope that they will solve real problems like energy, like solar energies, make solar energy more usable and such things for societal purpose. So we want to use them as societal purpose. That's the long term goal, and that's why we are trying to utilize properties which can arise in the system because of certain things which are beyond what we already knew, the one that we talked about, that we already learned until about 1980s or so. The 1980 is not a very rigid barrier. It changes over time, but we have developed science or condensed matter physics to a very good level up to that point, and from there, there was a shift in the understanding, and that's where this strongly correlated electronic system study of strongly correlated electronic system gained momentum. So, like for example, you might want to make a material which will conduct electricity without any loss, without any resistance, let's say, but at the same time, we don't want it to conduct any heat. So, can we make such materials? So, that's the kind of question we have been asking now. Or that's basically keeping the condensed matter physicists busy more in the present context than the way it did in the past. So now I will take you very quickly through some of these recent surprises, which are not very well understood areas of condensed matter physics, but which are very rapidly emerging areas of condensed matter physics. People are trying to gather more knowledge. So one very and they're fundamentally different from what we knew, and I'll try to highlight that. So so far I have talked about transitions which occur only by breaking some symmetry. So the question people asked, and people actually asked it long time back, and this is actually beginning of 1970. So it's about 1975 when people worked out these things, that can there be phase transitions without without breaking of any symmetry? And the answer is indeed yes. And this actually got the Nobel Prize in 2016. I forgot to write the name of these people. This is Kostelis, Thouless, and Duncan Haldane. Right. So these three got Nobel Prize in 2016 because they came up with a way to understand phase transition, which are beyond the paradigm of symmetry breaking phase transition that we described. So how does this phase transition occurs? That's really fantastic and novel, in the sense that they occur because of something which is very strange object. Some singular object which are called vortices. So in this case, this is this is a vortex, so which is like a swirling water, let's say. This kind of picture you can see oftentimes if you are watching weather report, for example. You see this kind of cloud and some swirling wind for cyclone and things like that. And for the simplest thing, where we might all be observing them, is that when you flush your toilet, you see this kind of water circling around and making some conical shape like this. So that's a vortex. So it has a directionality of the swirl. And so what happens in certain system, where there is no symmetry which breaks, however, the system creates within itself something what are called topological defects. Topological defects, one example is like the vortex. So here what I show is a topological defect which is called a vortex, and another one which is called an anti-vortex. So these are very similar to each other, with the only difference that if you go around the circle in a clockwise manner or counterclockwise manner, whichever way, so this will circle along the direction of your path, and in this case it will try to go away from the direction of your path if you're going in the let's say clockwise manner. right? I mean, so these two are called vortex. This is called vortex. This is called anti-vortex. So now you can imagine very easily that if they come and stay very close to each other, then the direction of this field, which is given by arrow, will have some changes in this region, but otherwise they will all point in one direction. However, if these two objects start moving apart from each other and further apart they move, they completely disrupt this field. I mean, the field that is given here, field meaning this vector field, which is given by an arrow. So there is a different class of phase transition then, which do not occur because of any breaking of symmetry. Symmetries do not break. However, what happens is that the topological defect, I mean, typically they always come in pair like vortex and anti-vortex, which were bound together in one phase, and they get separated, they get unbound from each other in a different phase, and thereby completely disrupts some particular property, like in this case the arrangement of the field pattern. So these are called topological defect, for reasons which is not so important now, but it will come probably very quickly. So such unbinding of topological defect is the reason behind a different class of phase transition than symmetry breaking. So I think at the time when they studied, they just wanted to find a different way of finding phase transition than symmetry breaking in 2 dimension for other reasons. I don't want to get into that, but they found it. But then it turned out that these are extremely important for much broader, from a much broader perspective. So, for example, so now, why are they called topological defect, or what is topology? So I will quickly explain that topology. I mean, to a topologist, a cup or a donut, I mean, some object like that, a tube of a bicycle tire, let's say, they are equivalent objects. So what does that mean? So topology is a branch of mathematics which studies the geometrical properties of matter, but it's not a geometrical properties in the sense of studying a circle versus isosceles triangle versus equilateral triangle versus, let's say, a square and things like that. They don't do that. They want to study the broad properties of different geometrical shapes which are made by deformable object like a rubber sheet, for example. So this is precisely what is meant here, that a cup is same as donut. So you can take a cup and then you can deform it continuously in slow step, and then you can make it like this. So that is why they are topologically equivalent. These two objects are topologically equivalent, but this is not same as what called pretzels, because they have three holes in it. By smoothly transforming the shape, you are not going to change the number of holes through it, and that's why cup and these objects are topologically equivalent. So that's the basic idea of topology. There are many other then the number of holes you have is called genus, the number of holes, and so topology is characterized by the number of holes, for example. There are many such topological objects or topological defect. Like in lattice, it might so happen that you have one row of atoms which suddenly end somewhere. So that makes a topological defect. Topological defects are such that which cannot be mended very easily. So, I mean, you cannot just remove a topological defect by doing some small rearrangement. Just the way you cannot remove an additional hole just by making a small rearrangement. You cannot make a regular hole other than by punching another hole. So it's just like that. You cannot really get rid of the topological defect. There are other topological defect. We all carry topological defect in our fingers, finger marks like this. They are called terminal points, which are like this in polymer physics language. They appear. So these are all examples of topological defects. So now, why are topological defects important? Topological defects important from the following perspective. I mean, I said that the topological objects actually share many properties which cannot change by simple changes. Simple changes meaning discontinuous changes. And they can change only by making drastic changes like punching another hole. So now let's come to something called quantum Hall effect. a particular phenomena which occurs because, I mean, there is something called Hall effect, where you talk about development of a voltage in a transverse direction of an applied magnetic field and carrying electric current on a sheet of metal. So this is a metal, you are passing current through it, and then there is a cross field that you have. By cross field, I mean the field which is perpendicular to the direction of current. So then what happens, there is something called a Lorentz force, for which opposite charges get accumulated into different sides of this plate, two-dimensional plate. So this charges getting accumulated creates a voltage drop across this direction, which is called a Hall voltage, and that gives rise to what is called Hall resistance. So that's the classical Hall effect. So what turns out that the Hall resistance, I mean, in classical sense, will go linearly with the magnetic field strength that you have. So it turns out that gets actually quantized, meaning you can, I mean, if you go to very high magnetic field, then something special happens, and this Hall resistance get quantized. So that's something which kept physicists busy, and it actually gave 2 Nobel Prizes in physics on Hall effect overall. I mean, okay. So now, what I wanted to tell you is that, so what is special about the strong magnetic field? So what happens in a system like this, plate like this, if you put a very strong magnetic field which you are putting on the plane of the paper, perpendicular to the plane of the paper, if the field is very strong, then electrons start moving in what are called cyclotron orbits. So that originates from the same Lorentz force physics, but because they start circulating in small loops, and the loops get smaller and smaller, larger the magnetic field, so these electrons cannot participate in a transport, because they get localized in some small region, and larger the magnetic field, smaller the region of their localization is, right? So, and if the electrons get localized, they cannot carry current from one end of the system to the other. While that is true, there are some very special electrons which lives only at the edge of the system. So they don't get localized, because they try to get localized, but then they hit the boundary, they get reflected, and then they start moving like this, which are called skipping orbits, right? Skipping orbits, because for the reason you can see, they are doing like a skipping, and they go around the system like that. So it seems that in quantum Hall system, you have some special situation where the states which are in the bulk of the system, or electronic states which are in the bulk of the system, they become localized. On the other hand, there are some special states which actually remain completely delocalized. I mean, where the electron move around the sample, which are called the edge state, because they live at the edge of the sample only. So it turns out such edge states are fundamental in the transport in quantum Hall effect or quantum Hall system. Now, if you think of it, so this is very similar to the topology that we have described here. In fact, one can find a topological invariant for quantum Hall effect. The reason is very simple. The details of the material does not matter for the transport. I mean, you can have more disorder in the system which will go in the bulk, it doesn't matter. The transport will happen only in a small region, and that doesn't matter. If you make the system little wider or little narrower, it doesn't matter. All that matters is how many electrons are there which are doing a transport like this. So that way it is similar. So that is topology, that has a topological property, topological invariant, which in this case are called Chern numbers, I mean, which are again technical object. But so that is the part which actually has profound effect for the quantum Hall effects in general. Then there's spin quantum Hall effect. I mean, various different parts which work in this quantum Hall system because of the topological property of the system, which was not real. I mean, which wasn't appreciated as much, I guess, in the past, but now it is very well known. And then people are using the topological connection to other systems, not just quantum Hall effects. So, for example, people talk about topological insulator, which are systems which are very similar to this. However, there is no external magnetic field like quantum Hall effect, but the role of external magnetic field is played by what are called spin orbit coupling. So some kind of interaction which are there in the system. Then there are other interesting things like entanglement or quantum coherence. So this is the extent of quantum correlation between different parts of the system, leading to observable. I'm so sorry about the spelling mistake. So this would be observable properties. So let us discuss very quickly about it because I'm running out of time. I understand. So there is something very special about quantum mechanics, which leads to what are called superposition of constituent particles. So even like electrons, so you can think of an electron being passed through this kind of a ring structure brought in from here, and then the electron gets split into two parts. I mean, electrons are both particles and waves, as you know, according to quantum mechanics. So some component goes from this side, some component goes from that side, and then they reunite and then they superpose, and that superposition could be constructive. I mean, that leads to what are called interference. Interference of electron, and that leads to they interfere constructively and destructively, and this leads to what are called diffraction, single electron diffraction. That is something that people have realized many times over the years. So that's the superposition principle, that it mixes itself. Electron mixes with itself. So this is a funny cartoon structure picture of a Schrodinger cat, which is a superposition, quantum superposition of a live cat versus a dead cat. But let's not get into that. I don't have much time to talk about it. However, there is something. So there's something which is very important and which made this subject very popular. Is that for because it has some possible application to what are called quantum computing. If you want to talk about a classical computer, CAL has gone down, sorry, because of sizing. So in classical object, I mean, let's say there's something which is called a bit, which will carry the value either 0 or 1. I mean, computer always talks in terms of 0 and 1, classical computer, as you know, and they will be colored as yellow or blue. But if you are talking about a quantum bit, which is something very unusual, in the sense that because quantum objects will follow a superposition, so it will be a superposition of 0 and 1. As a result, it will have a color which is not discretely yellow or blue. It will be some continuous change of blue and blue here and yellow there, and some bluish yellow or yellowish blue, whatever you want to call that. It will be a quantum superposition of that, and that's called a qubit. So such qubit, if exist, if can be created, have enormous implication for what are called quantum computation. But I'm not going to talk about quantum computation for the moment. Let us try to talk about entanglement. So as I said, it is the quantum correlation, some beautiful braiding, like this beautiful braided hair of this girl. So what does it do? So entanglement is a measure of quantum coherence. In entanglement, the properties of two particles are intertwined, I mean, just the way of this braiding, intertwined even if they're separated by a great distance from each other. So that's something very, very interesting. So it is intertwined like some cartoon picture that is shown here. So let's think of a red ball and blue ball. So these are two different balls which are different properties. Now let's bring them, they were very far from each other. Now you bring them close to each other, and not just bring them close to each other. I mean, you'll make them interact. So that is very important. So you have to make them interact, and then thereby they get entangled. By that, I mean that the red ball and blue ball, they start sharing properties through interaction. They get intertwined quantum mechanically. So that's what is, they get entangled at this stage because of interaction, some kind of interaction. The funny thing about quantum entanglement, or exciting thing about quantum entanglement is that once they are entangled, now if you take them apart from each other, as far as you go, they remain, I mean, the color remains as just before, will remain bluish red or reddish blue, but that will remain like that even if you have taken them very far from one side of universe to other side of universe, and you can't tell whether it is blue ball or red ball. However, what is very interesting, I mean, which is showing here, I mean, in some kind of a GIF file, that, I mean, so there will be this color is blue red is something like these balls. When they're very far from each other, like two ends of universe, if you measure the color of the ball here, the moment you measure, this will not be a bluish red. It will be either blue or a red one. Now, the moment you know that this is blue as opposed to being red, you immediately know the other ball which is taken away, the other end of the universe was a blue one. Or rather, if this was blue, the other one will be a red one. So it is like you were, I mean, so you didn't know that they're blue or red individually at the beginning, but once you know about one, you know the other. So this is what Einstein termed as spooky action at a distance. And this is because this is a result of entanglement. I mean, the fact that they're quantum entangled, and so quantum entanglement is something which is interesting. They can be there can be several uses, including, I mean, so not only in quantum computation or quantum information theory where entanglement were first considered, but even it turns out that entanglement could be a very good measure to even identify phase transitions in condensed matter physics. So that's the part about which condensed matter physicists are very excited. Entanglement is not always observable because of some other thing that comes about, which are called decoherences, which actually breaks the quantum entanglement nature. And there are people who are in doing active research to see how one can fool the decoherence and uh, see the profound effects of entanglement. So, and what I have written at the bottom, that this expected to have application, the quantum entanglement application to energy technologies, quantum computation, cryptography, and telecommunication, teleportations. But beyond that, I personally think that they actually serve as probe to discover new phases and new phase transition that has been established. I mean, established that they can. Now, whether they can help to find a real new one, I mean, they're benchmark to do well for the known phases and phase transitions. We just wait to see their application to some new physics. I mean, so this brings me to the end of the talk. I'm not sure how did I do with the time. I guess I have taken a little more time, so I won't go into a very detailed conclusion. So I'll just say that interacting many particle physics is described by champion physicists in various different ways. I mean, in poetic language, in some sense, more is different. I mean, more. I mean, if you have more, they're just different. It's not boring. I mean, that's what make the the area more exciting. This is by Philip Anderson, one of the champions. The other person, I mean, so Pierce Colbert, who is a fantastic physicist, and you might have seen. He maintains a very good physics website. He is in this. Uh, Rutgers University, and maintains a fantastic web page and interesting physics resources. So he described this as an incomplete revolution because there are a lot more to do in this revolution. There are a bunch of materials which are all part of condensed matter systems, study of condensed matter system. They're valuable because linked to material science, chemistry, and engineering, something that I mentioned perhaps somewhere along my talk. And recently started developing overlaps with biology, biotechnology, medicine, and various other areas. So it's a very important so this technology is a very important motivation for being associated with condensed matter physics. And I mean, it is then only fitting that it is the largest subdiscipline of physics. I mean, largest is not always very easy to quantify, but one third members of American Physical Society, if you think of APS, because they have a very systematic accounting or bookkeeping of a member. One third of those members belong to the division of condensed matter physics, and this is only fitting because there are a lot of excitements, very diverse excitements in the perceivable scale of phenomenology. So that keeps the subject going, and I'm sure that we all will contribute. I mean, I would expect many of you students present here will explore and discover many new things in condensed matter physics. So with that, I have come to the end of my presentation. So I thank you for your attention, and I'll be happy to take any questions that you might have. And I'm sorry if I have overshoot the time in a significant way.
So thank you, sir, for your wonderful presentation, sir. So students have learned a lot of things by your presentation. So if you allow us, we can start our discussion session, sir. We have got some
Sure.
question in comment. So first question, whether BEC is coming under condensed matter physics.
BEC, Bose-Einstein condensation. Yes, it is.
Yeah.
It comes under condensed matter physics, certainly. Yeah, I don't know whether it is studied in any other branch of physics. Like superconductivity is studied also in particle physics, because the fundamental reason behind the transition in superconductor has similarities with other particle physics system, I mean color, superconductivity, and all that, but those are different. But for BEC, I think it is studied only within the broad area of condensed matter physics. I mean, in particular, in more recent time, they're studied hugely in an area called this optical traps, or the ultra cold atom system. I mean, which is used uh, using the norms of BEC. Yeah. So
thank you, sir. We have another question. So there are analytical model to understand classical and quantum spin system. So is there any chance that other developed models are developed in the future to describe their characteristics in a much easier, accurate way?
so I couldn't hear all of it. You
Okay,
talked about
I can
classical and
add.
quantum.
If you can stop share, then you can see the question.
Oh, okay.
I
So
have added.
how do I stop share screen? I mean, how do I?
So please go the StreamYard screen, then you can see the screen.
So
Come into the StreamYard.
okay. StreamYard, huh? So there is a share screen. So how do I
No,
stop?
so you should there may be the option stop share. Okay, I
So
can.
it says share screen. I mean, it doesn't say.
No. So have you stopped it? So
You
can you
stopped it?
see?
Yeah. So that is fine.
Okay.
So
So there are I can repeat it. So there are analytical model to
oh, I
understand
see. I see.
classical.
Now I see this question. So there are analytical models to understand the classical and quantum spin system. So is there any chance that such other developed models are developed in the future? Such other developed model means the classical and quantum spin system future to describe characters in a much easier and accurate way. Uh, Okay, so I don't know whether I have understood the question fully, but the understanding of classical and quantum spin system, there are some. So, so the thing is, okay. So in condensed matter, you try to understand something not just for model. So there, you can always create a model, and you can understand the properties of the model. But the real challenge is whether that model has relevance for some real material. So that's where the question become, I guess, the more interesting. And certainly there are several magnetic materials for which classical spin model as well as quantum spin model had been useful. That is certainly true. But then there are other interesting phenomena, or some of which are, I mean, so that that exist. Like, so for example, I can tell you one name, I mean, which quickly comes to my mind. So people believe that there are some new phase which are called spin liquid, quantum spin liquid. So that's a very strange object. I mean, there are properties of a spins or collection of spins. However, the spins do not order. I mean, they are always in a quantum mechanical fluctuating state. So if you ask about it, I mean, so yes, there are fewer models, not as many models. So is there a model for understanding spin liquid state? The answer is largely no. So that's a subject which is being developed. So classical and quantum spins is something. It's not that a model describes everything. So obviously there are very successful models, like you have in quantum model. I mean, there are so-called Heisenberg model, or Heisenberg spin model, or even more exotic model in quantum condensed matter physics called TJ model. So, which is a Heisenberg model with some kind of a kinetic energy term like hopping. So that has been used to understand quantum antiferromagnet. Their classical model like Ising model, with which we understand various different things. So there are many things we understand, and then there are many things we don't understand or you'd like to understand. So obviously, it is natural that we understand the simple things first, and it is more difficult to understand more complex things. So there are things like that. So, and then people would like to understand all of it. So there are several things remain to be understood. So is that anywhere along the line of your question, or I misunderstood the question completely? So the name of the student was there, student, or I don't know if it is student or not, who asked the question. I cannot hear. Hello. Okay.
Sir, can you explain? Can you explain what is basically meant by the term?
Okay. So this is very interesting question. So ergodicity is a very fundamental concept of statistical mechanics. I mean, statistical mechanics is based on ergodicity principle. So ergodicity, I mean, this is a very common term, I mean, which I didn't talk about. I have some interest, and there's something called many-body localization, which has become a very popular, very popular topic of study these days. A very important area of study. So the thing is that if you have a system, if you leave the system, and if it is a many particle system, there can be many different states. I mean, the phase space of the system is very large, right? I mean, because you know, so it's a multi-dimensional system. I mean, if you have n particles and in 3 dimensions, there are 3 n-dimensional phase space. So in this phase space, a particular state of the system is just a point. So now if the system is in contact with a heat reservoir, then it is expected that it will exchange energy with the heat reservoir, and the system can be, I mean, when the system is in equilibrium, the system will actually move around the whole phase space. It will access all points of the phase space. So when that happens, the system is said to be ergodic, that the whole phase space available to the system is accessed by the system in its equilibrium dynamics. However, there are systems which may not do that, and those are okay. So the thing is, this is also called thermalization hypothesis. I mean, ETH is what it is called. So, in the sense that in system which is in equilibrium and which is ergodic, will thermalize, in the sense that it will access all possible states available to the system in the whole phase space. However, there will be systems which will break that. I mean, which can break the ergodicity, which means that even in contact with heat reservoir, even at the highest temperature, system will not access all the phase space. And how the system accesses different parts of the phase space, because so if a classical system, for example, is in the contact of heat reservoir, there is a energy that is given by the heat reservoir to the system, which is the KBT. I mean, equipartition theorem will give you the energy, and with that energy, because the system is always kicked by that energy, so it tries to access all energy states possible. So when the system does not do that, then it is called a non-ergodic system. So somehow the system does not access all possible phase space available to it. So the system remains, I mean, it can never reach equilibrium, and such states are possible even at the very large temperature. It is possible to have a system, particularly quantum mechanical system, which will be non-ergodic. So such a state is called, for many particle interacting system, quantum mechanical system, that is called a many body localized state. So if I have to give you a simple example of a classical state which is believed to be non-ergodic, I mean, is certainly non-ergodic over a very large length scale, is what are called glasses. The glasses like window glass. Glass is a state which is not solid, right? I mean, this has all the symmetries of a liquid, and one believes that the glass will become liquid if you wait for infinite time. So glass is a state which is always relaxing, but it is not going to a liquid state. So the fact that glass is a system which is trapped, I mean, which is a liquid, but which is trapped in such a situation that it cannot move out of its current location, or location in phase space, or you can say that in energy space it is localized. So it cannot access all equally likely energy states which are and get trapped in some energy, in a higher energy state, or some energy state, I mean, which cannot, excuse me, which, I'm so sorry. Yeah, so uh, that's what is called a non-ergodic state. So understanding non-ergodic states and developing, and people believe that there is a phase transition that takes place between ergodic state of matter to non-ergodic state, and that is studied in many body localization. So that's something. How quantum properties fit in hard condensed matter. So yeah, so actually this part I probably could have mentioned somewhere. So it's the quantum which matters for hard condensed matter. So hard condensed matter essentially is a uh, quantum mechanics plus statistical mechanics, thermal physics, I mean. So in the sense that in hard condensed matter, what we try to do is that we try to find the quantum states, quantum energy states, and then we carry out the Boltzmann distribution. Like, at a given temperature, you will populate a particular energy state with the probability of e to the minus beta e. That's just like a classical statistical mechanics also. Only difference is, what is this e? This energy e could be either a quantum mechanical energy state, and which is what matters. I mean, this is what matters for hard condensed matter. On the other hand, if the energies are just the classical configurational energy, and that is sufficient to answer all the interesting questions about a particular phenomena, then that falls under the purview of soft condensed matter. Whereas if the quantum mechanics is important, or in other words, if there are quantum 0 point motion, that becomes a subject of a hard condensed matter. So this, I guess, it will be good. I mean, I think I have another talk after a week or so, right?
Yeah.
Right.
On
So
6th of
there I will.
November.
Right. So 6th of November. So that's where I will. Uh, 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 so that's when I will take an example of a very similar system where quantum effects. How can quantum effects change the nature of the classical phase transition and make it a quantum phase transition? So that will be part of it. So that, I mean, with that example, probably it will be easy to discuss this question. So if you are present, I mean, this is I do some kind of an advertisement that you should come for that talk to get a little more direct answer. But
Sir,
okay, I mean,
so
if you decide
we
otherwise,
have
that's fine.
another question, sir. So did
Yeah.
you get the
So did
link
not
between
get
the?
the link between the phase transition and quantum entanglement. Very good question. Yeah. So I actually So okay, so the link, I don't know whether the link is very well understood yet. The question is that, okay, so I talked about phase transitions, and so what can measure a phase transition? So there are various measures. So for example, if it is a metal or an insulator, is measured by calculating what are called conductivity, right? So we know that. So this conductivity is the ability for a material to conduct. I mean, J equals sigma E. We know this. J is current, and then E is the electric field. So in a applied electric field, if I have to drive a current, then it is related between J and E as a conductivity. So conductivity can be calculated in various ways. I mean, it can be calculated as a response function. So there are many response functions. So most of the time we try to understand a phase of a matter by perturbing the matter. So this is a fundamental concept, and there is a whole topic area of learning which goes by the name of linear response theory. So we try to understand, we try to characterize a particular matter by, let's say, by looking at its resistivity, conductivity, some magnetization. So all these means that I perturb the system by some kind of a field. I couple it to something, some vector potential, some scalar potential, something, and then we see that by coupling it to the vector potential, what changes occurs, and that is quantified by some kind of a response function. All right, so that's the kind of response function we traditionally measure in condensed matter to say whether which phase it is in, and the conductivity will give very different values for a metal versus an insulator. An insulator, the conductivity will be zero, and in metal it will have a finite value. Okay, so now what has been found, and that has made it very, very exciting, that this traditional way of calculating these properties, which is the response function, which is good, but there are some limitations. There are some phase transitions where these standard measures or metric of a particular phase doesn't work very well. So that's okay, that can happen, and then one has to develop other understanding. So it turns out that when you have the phenomenon of quantum entanglement also have some measures. I didn't talk about any of them, but there are, I mean, and there are very standard ones like entanglement entropy, and then there is something else called fidelity, but these are mostly theoretical tool. I mean, you can't, I mean, it's not clear whether you can measure. I don't think there is any direct measurement of entanglement entropy. For example, entanglement entropy is a measure of entanglement. So similarly, there is something called fidelity, but these are all measures which are theoretical. I mean, in a model you can quickly develop that. So the question is, so does these kind of measures, which are not a response function, can also measure can play some role like an order parameter, meaning that also changes to identify the phase transition? And it turns out that they do. So entanglement entropy or fidelity, I mean, these are the two objects that I didn't explain what they are, and this will take time, but let's not get into that details. But the main idea is that there are measures or metric of entanglement which can identify a phase transition, or which can identify a phase versus another phase. So this has been documented. I guess why they can do that is a question that one would like to understand. And also, I mean, and the development occurs hand in hand between theory and experiments. And then there are all these measures that are mostly theoretical so far. One is trying to see whether one can measure that. So like establishment of that tie will be the question that Gargi asked, is something which is a nice problem for you guys to explore in future. Okay, so another question: how much are experiments related to solid state physics and material science department on the concepts of condensed matter physics, or can we say that both of them are interrelated with each other? Yeah, both of them, meaning the solid state and material science. I mean, solid state physics is same as condensed matter physics. Excuse me. It used to be called solid state physics earlier, and I mean, so there is not really much difference between this thing. But what is the relation between material science and condensed matter physics. That's a very, very interesting relation. uh, just give water. Yes. Okay. So so there is a so this is the relation one would like to establish. One would like to believe that these two subjects will enrich each other for the development. So material science is the job of material science is what I was telling, that to develop new materials, smart materials or functional materials. So that is uh, to a large extent, in my opinion, what I understand is that the development of material science occurs because people just try. I mean, I don't try to give an impression that it's just a trial and error process. It's not. There is a educated guess that people take, but the motivation is to make new material which will be useful for application, energy application or other application. So for example, one thing that many of you students probably know or heard somewhere somehow, that this high temperature superconductivity is a subject which is an unsolved problem, in the sense that the way people understand low temperature superconductivity or BCS superconductivity, we don't understand that theoretically at that level. On the other hand, people have experience, right? I mean, so are there high temperature superconductor? The answer is yes. So then people try to do something based on some knowledge, some leap of faith, and then they make. I mean, there are many high temperature superconductors which are made. The hope is that if condensed matter physics come up with a detailed understanding of the physics of high temperature superconductors, I mean, if it becomes solved problems, there will be a lot better predictability, or lot better control with which material science can make these materials. So it's the knowledge of, I mean, so this way material science will gain from the knowledge of condensed matter physics, and the opposite is also true, because depending on where material science is growing, it gives a clue to condensed matter physicists to understand, to realize what is the problem that they will try to understand, which will have a larger impact. So these two should go hand in hand, and they go hand in hand by and large. Yeah.
Thank you, sir.
Okay,
We
so
have
then
another question.
recently a paper came out regarding the achieving of superconductivity at room temperature. Right. So will it have any kind of effect on the existing concept regarding super? Fantastic question. So I'm really glad that you are keeping track of that. So yeah. So the thing is, this is a very interesting development. I mean, this is a very recent development, as you know, though it is not as recent. I mean, this is a series of experiments or theoretical concept that so it started long back with some work by Neil Astroff, and you probably know that there is a condensed matter physics textbook by Astroff and Mermin, very popular book. So I think it is called Solid State Physics. I forgot the title of the book, but it is more popularly known as Astroff Mermin book. So it's the same Astroff. I mean, there's Neil Astroff. So he's suggested by theoretical calculation long back that if you are trying to look for high temperature superconductivity in some way, I mean, under certain setting, they should look for halide materials. I mean, hydrogen. I mean, some materials to do with hydrogen atom and halides, and that's the direction which people have been pushing, and they have succeeding to achieve room temperature superconductivity. So now the question, sorry, the question was, I mean, I'm just acknowledging that. So will it have any kind of effect on the existing concept regarding superconductivity? So the thing is, okay, so we understand. So the part of superconductivity that we understand very well are called metallic superconductors. So that's the simplest superconductor. So you take lead, aluminum, iron, all these metals below some very, very low temperature will go superconducting. I mean, they go superconducting. That's very well understood. So, and that is mercury and all metals actually. So they are understood in terms of VCS theory. That's the only part of superconductivity which is understood, but they typically occur for transition temperature of the order of 10 less than 10 Kelvin, and in some cases which can be still understood in terms of BCS theories, maybe there are 30 Kelvin or 40 Kelvin. I'm just making up some number. So the superconductors with transition temperature of that order can be understood. So the same superconductivity theory cannot understand uh, hopefully cannot understand the superconductivity which will be superconducting transition temperature, which is room temperature, that is 300 Kelvin or 273 Kelvin, something like that. So that's a very high temperature. So if you think that, okay, in the same BCS model, if we tune the model parameter by some amount, then I will change the TC by some amount. So if you have to do that, if you want to do that, that will require so much of tuning of a parameter which is unreliable. So that certainly does not work to understand high temperature superconductivity. So I believe that this will lead to a new, I mean, not just me, I mean, many people believe that this will lead to the understanding of, if one gets a theory, I mean, this theory will be a different theory for understanding high temperature superconductivity. So it's just a different mechanism for obtaining high temperature superconductivity that is different from the very well established BCS theory or Martin Cooper-Strifford theory. Yeah.
Thank you, sir, for your answer. So one more question. So it's just the question of question. So please explain once more.
Please explain once more qubit. Okay, so I didn't explain qubit. So I was just saying that if you I mean, for classical spin, let's say, if you're thinking of a classical spin by that, is it okay to say spin? I mean, do you have a feeling for what spin is? So spin, you can think like an arrow of a given magnitude, which, let's say, take unit spin, meaning the size of the, it's like a vector, which has a value of unit magnitude, meaning the length of the spin is 1. So now that spin, if it was classical, it is believed. Ising spin, for example, is a classical spin that will have two values. I mean, either up or down. Okay, so that's the classical spin do. So it can be either in up state or down state. So that is oftentimes termed as the bit, classical bit, which are like zeros and ones. So this binary number system, and what is that other thing called regular number? I'm forgetting the name. You can convert the regular integer to binary number and vice versa, right? So computer works in binary. So classical computers, I mean, all computers that we know are classical computers. So they work in terms of zeros and ones. On the other hand, a quantum spin cannot only have this up and down, but it can have a superposition and up and down, which will be the spin which will just be anywhere which will rotate anywhere within the unit sphere. Unit sphere meaning the sphere with radius unit. That's the size of the spin. So you can take advantage of the quantum superposition to have more states of a bit than just being 0 and 1, if you can realize that. I mean, so whether one can make it or not is something that people have actually made qubit, but whether that is at the scale where one can do a quantum computation, no, the answer is no, to the best of my knowledge. So the thing is that, so qubit is going to, so because it's a quantum object, it will follow the quantum superposition principle, and it can store information which is more than 0 and 1, but anywhere which is some alpha times 1, alpha times state 0 plus beta time state 1. I mean, where alpha and beta are two complex numbers. I mean, such that the norm is preserved essentially. So that the size of the spin is preserved. So that allows, I mean, if that is possible, that allows the bit, that particular bit, to inform lot more information than what a classical computer can store, classical bit can store. And that so what is the advantage if it does that? So there are certain algorithm, certain uh, uh, prime factorization algorithm. There are certain algorithms which are which can be shown will take infinite time in classical computer. Infinite time is not really infinite time; they're exponential in time process for classical computer, which can be made into a polynomial time computation, which means that which is tractable under quantum computation. So one can do much bigger or much more sophisticated calculations in quantum computer using, if you could realize the qubit, I mean quantum bit, in large scale, so that you can make a computer out of it. And that's what the goal is. I mean, that you want to solve problems which are essentially not solvable by classical computers.
Thank you, sir. We don't have any more questions, so we should conclude our discussion session, sir. So thanks for your wonderful presentation and exciting discussion session, sir. I think students have learned a lot of things from your lecture and discussion session. And we'd like to say thanks on the behalf of the Department of Physics, Pabna, University of Science and Technology. And we will arrange another webinar. So we have another webinar on 6th of November. So thanks again. Yeah.
So I will look forward to it. I'm very happy to be here. It was my pleasure. And please, I mean, I forgot to put. I mean, I'll do that in my next webinar. But I mean, please share my email address with the students. So if anybody has any question, they can certainly write to me. I'll be happy to address.
I'll share your email to all of my students. So thanks again. Bye for today, and see you on 6th of November.
Thank you so much. It was really a pleasure to be here.
Yeah, it's my honor and privilege to host you in my physics webinar. Thanks again, sir.
Bye. Thank you. Bye-bye.
Good night.